Welcome to qnawire.
So we're going to be looking at flow now. We know that for some flow, if we know the density at some point and the velocity, then the net rate of outflow through the substance will be the double integral of f dot ds, and that is going to be where f is equal to rho x, y, z times v, the vector x, y, z. So with that in mind, we know our v is z y squared x squared, and we know our density is constant at 870 kilograms per meters cubed. So that tells us that our f will be 870 times those other values, 870 times z y squared x squared. And then if we want to parametrize this surface in terms of cosine, how we can do this is r u of v will then become the vector 2 cosine u 2 sine u v. So f of r of u of v is going to end up giving us 870 times v 4 sine squared u and 4 cosine squared u. Then we also recognize that this is the same thing as this right here, where n is the normal vector. So since ds is equal to the cross product of ru, the magnitude of that dA, we know that the flux will only be defined if the surface is orientable. So let's try to find, this will be nda. So we'll try to find the normal vector, which is nda is the same as ds. So finding the normal vector, we get that when we parametrize the cylinder, when we take r, the partial derivative of r with respect to u, so partial derivative of r with respect to u, we end up just getting a negative 2 sine u and a positive 2 cosine u by taking the derivative of this with respect to u and the derivative of this with respect to u, as well as the derivative of that with respect to u. And then when we take the partial derivative of r with respect to v, we get that these will both be 0, and then this will just be 1. So when we take the cross product of all that, we end up getting that the cross product is 2 cosine u 2 sine u 0. That's the cross product of ru cross rv. And then this right there, dA, is the same thing as ds. So as a result of that, we can now write this up here as going to be equal to 870 times this, or 870 times this, dotted with this vector right here, dA. And then once we do that, we'll pull out the 870 and we will take the dot product. So pulling out the 870, and keep in mind this is actually going to be an integral. So this will be a double integral. We'll put the 870 out here, and then we'll take the dot product, which we end up getting to be to the cosine u plus 8 sine cubed u dA. Since u is between 0 and 2 pi and v is between 0 and 1, we can set our bounds to be 0 to 2 pi and 0 to 1. And this will be dv du. Then evaluating this first integral, we end up getting the rate of outflow. So this all will become cosine u plus 8 sine cubed u du. And this will go away now. That's what we end up getting. And then we can also, to make this more clear, this will be sine u cubed. We see that we end up getting 0. And we can confirm this by recognizing that this integral right here is going to be 0 because the rate of outflow is 0. So this will be times 0. We get 0 as the net rate of outflow of the fluid.